All right, AP Chemistry, this is the answers video for day 136 on electromagnetic waves. It says it is due on Monday, March 24th. I'm going to push that back to Tuesday, the 25th. So please have that done by Tuesday, the 25th. Thank you. Okay. And, okay, get started. So you have a pre-assignment on that. I'm not going to check that. Just get that done. And then I'm going to go to the problems here. I'm going to do the A problems. You do the B problems, which are identical. If there's not an identical problem, I'll do that as well. I feel like on some of these, there's not enough space. So you can do the first part on the sheet here, and then conclude it on a piece of lined paper. Just be sure you number the problem so that I can see which one it is. I'm going to go ahead and do the whole thing on lined paper. Okay, so we have a 7A, so label that. Okay, so an FM radio station has a frequency of 88.9 megahertz, and that's 10 to the 6th hertz, or cycles per second. What is the wavelength of the radiation in meters and nanometers? All right, so go ahead and first thing is write down what you're given. Or what you're looking for, either one. I'm going to go ahead. So it's asking us for wavelength. So just write it like that. And then we have a frequency. So I strongly prefer that you write frequency as 1/seconds, because you can do a unit cancellation in the middle of the problem. At the end of the problem, you can leave it as 1/seconds or call it hertz. All right, then the number we always have involved with electromagnetic waves is the speed of light. Right, so we have a formula from the formula sheet. That's right here. All the formulas you need are up here in this box. Those three formulas, and then Planck's constant and the speed of light right there. So speed of light equals wavelength times frequency, lambda times nu. Come over here and do algebra if you need to. Now you can come back here and solve the problem in the middle. 1/seconds. The seconds will cancel, and the meters will be the only units standing. Okay, and that gives you 3.3 meters. That's fairly long for the length of an electromagnetic wave, but radio waves can be that length. Radio waves are the type of waves that would actually carry TV and radio signals back in, the 50s, 60s, 70s, before people had do it the way they're doing it now. Okay, so there's your answer. Now, a question also asks, what is the wavelength in meters and nanometers? So we're going to come down here. And there's 10 to the 9th nanometers for every 1 meter. So I'm going to come up here. That should be a time sign. I'll write the equivalency the way we always did. I'll just go ahead and do that. 1 meter equals 10 to the 9th nanometers. Okay, so we put meters on the bottom to cancel. All right. Now the next problem, 7B, is exactly the same. It's giving you a frequency. It's asking you for the wavelength in meters is good enough. I had some of you do it in nanometers as well. This one, just leave it in meters. Okay, we go on to 8A. I'm going to do the A problems. And you do them with me and then do the B problems. So let's go ahead and read it first. Violet light has a wavelength of about 410 nanometers. What is the frequency? Then they want you to calculate the energy of 1 photon of violet light. And that is, that's what these equations do. These two equations give you the energy in 1 photon. So you can just write that here. Energy of a photon equals Planck's constant times the frequency. This one also, energy of a photon equals Planck's constant times the speed of light over the wavelength. So this relates the wave nature of light, frequency, to the particle nature, which is a photon. This treats it like a little ball of energy. This treats it like a long continuous wave. Same thing with this one. wavelength relates to the wave nature of light, long continuous wave, and this is the energy that would have in a little packet or a little ball of energy. All right, so we now know on this question both the frequency and the wavelength. We can use either of these equations. I kind of like this one because it has fewer numbers. All right, so go ahead and do that. Okay, so 410 nanometers for 8A. Let's go ahead and number it. We know C, and we are looking for the frequency, and we want to know frequency. Okay, so we're going to go ahead and write the equation. Come over here, do the algebra for frequency. Come back here and solve. Meters cancels. You end up with 1 over seconds. Okay, and that gives us 7.3 times 10 to the 14th. That's pretty typical. It's a very high frequency. It's hertz, but we're going to continue to work. This problem has an additional part to it, so I'm going to call it 1 over seconds. It doesn't matter. I prefer this when you're still working with the problem. So the next part of the problem, 8A, says, calculate the energy in 1 photon of violet light. What is the energy of 1 mole of photons? So when you have both frequency and wavelength now, I'm going to go ahead and use this formula right here. This one, because it's shorter than this one, and so we know Planck's constant right there, and we just calculated the frequency. And I like to write the subscript photon to be clear. That's what the energy is of 1 single photon. Okay, and what we get is 4.8 times 10 to the minus 19th. That's in joules because it's a measure of energy. And it's kind of a way to check your work. Is the energy in a photon of visible light is always going to be something 10 to the minus 19th power. Okay, and it's in joules. Okay. Now the next part of the question asks the energy in 1 mole. So 1 mole of anything is 6.022 times 10 to the 23rd. So we're going to come down here. Mole of photons, I'll just spell it out, equals, okay, you have this for 1 photon, 10 to the minus 19th, joules per photon. I'm not going to write that. I didn't write that up here in the answer, but it's joules per photon. And there are 6.022 times 10 to the 23rd. Photons per mole. Okay, so photons cancels and you end up with joules per mole. So we come on down here and calculate that. Okay, and that's going to give us 2.89 times 10. I'm going to lop off a few digits. We shouldn't be more than 3 significant figures here. Times 10 to the 5th power. And that would give us that many joules. Okay. If to express it in kilojoules, just slide the decimal over and it would be, okay, and to get kilojoules, which would be, divide this by 1,000 and you're going to get 289 kilojoules there. All right. Okay, let's look at number 9A. Okay, the energy of a mole of photons of red light from a laser is 175 kilojoules per mole. So we'll go ahead, 9A. And this is of a mole of photons. And I'm going to make that 175 kilojoules per mole. So I'm going to change it to joules per mole. So it's 10 to the 3rd. Kilojoule is 1,000. That many joules per mole. And it asks, calculate the energy of 1 photon of red light. Okay. So we're looking for this. So it's just converting, it's reducing it by a mole of photons. Okay, so the energy in 1 photon, just abbreviate that PHO. So moles of photons cancels and cancels. You end up with joules per photon. So just go ahead and do the calculation on that. We end up with the energy in one photon of visible light, of this red light, is 2.9 times 10 to the negative 19th. So look at that exponent negative 19 for the energy of a photon. So that's joules per photon. That's typically what you should be getting. In fact, always when it's visible light. Okay, we got that. Now it says compare the energy. What is the wavelength? So we need to do one more calculation, but we're going to circle this because it's one of our answers and we're going to need it later on. Okay, so it says what is the wavelength? And we have energy of a photon, which we just calculated. All right, what we don't have is frequency. So we can't use the wave speed equation. So we're going to use this equation here. This one right here. Okay, we're going to come over here and we're going to multiply both sides by lambda and divide both sides by the energy of a photon, which we know. Okay, so if I confuse you with the algebra, I divide it by this, I multiply by this, and you end up with this equation here. We know all of these. Okay, we're looking for a wavelength, so we see joules on top, numerator top, denominator top cancels, seconds on numerator top, numerator bottom cancel, and the only thing we have left is meters, so our units cancel. So now it's just be very careful with the math on scientific notations. Okay, so when we do this calculation, we get lambda equals 6.85 times 10 to the minus 7th meters. But we always express wavelengths of light in nanometers. So there is 10 to the 9th nanometers for every 1 meter. So meters cancels and cancels. And when we put those two together, we get 685 nanometers. Okay, and that's the way you typically, in fact, always express a wavelength of visible light. All right, now the question says, wants us to compare that to violet light. So this is typical of red light. So wavelength of red, if you look at the electromagnetic spectrum, it's right here around 700. And a wavelength of violet, which is the highest energy light. Okay, and if we go back to our previous problem, okay, and on the previous problem it tells us, it gave it to us in the problem, it's 410 nanometers. And this is nanometers. So again, somewhere between 350 for the highest energy light, violet in this case, and the lowest energy of the wavelength of red. Okay, number one, renumber these, I merged two assignments. Okay, so it says the most prominent line in the spectrum of neon is found at 865. It says others are 837, 878. These two are very close together, 878 and 1885. Which of these represents the most energetic? The most energetic is the one with the shortest wavelength, so write that answer out. And that, in this case, would be the 837. Okay, letter B says, what is the frequency of the most prominent line? What is the energy of one photon of this wavelength? So I'm going to go back to line paper. This will require calculation. Okay, so I went right away to converting to meters, 10 to the 9th meters. Okay, and of course we know the speed of light. And the formula is C equals, and we're looking for nu, so I think you can do the algebra by now on this. Okay, made a quick correction right there, 10 to the minus ninth, and go ahead and compute that. Okay, and we get the frequency is 3.6 times 10 to the 14th. That frequency is pretty typical for visible light, and that's 1/seconds or hertz. Okay, so that's the frequency. All right, next question is asking us and the energy in a photon of light. So you come on down here. And you can use either equation. I choose to use the shorter one for the energy of the photon. And this is joule seconds. So seconds and seconds cancel, you end up with joules for your final answer. Okay, and this calculation will give us 2.4 times 10 to the minus 19th. Again, we'll look for that minus 19th power, and that's a joules per photon. All right. Okay, so let's go on to 2 here. What series represents visible light, and what orbital do the electrons fall to in this series? So that's right out of the video. I'm going to ask you to watch the video and pick that one up. It has to do with the movement of electrons between orbitals. All right, express the following in nanometers. So we take this one, I'll do the first one, you do the second one. So that means it's going to be 10 to the minus 9th meters. Okay. So we made this number smaller by 2 places, -7, -8, -9. That means we need to move this decimal over 2 places like that. And you end up with 298 times 10 to the minus 9th meters, or 298 nanometers. Okay, so you go ahead and do the next one. 4 lists the 7 different colors of light in the spectrum, from highest on the left to lowest energy on the right. That's Roy G. Biv, spelled backwards. Also identify which end of the spectrum has the highest and lowest frequency, and which end has the longest and shortest wavelength. So I'll do one end for you here. The highest energy, which is going to be violet light, has the highest frequency. High energy, high frequency. It's frequency that determines energy, and inversely it has the shortest wavelength. So high energy, high frequency, shortest wavelength. All right, explain what determines the brightness of light. It's the number of photons. So if you have a lot of photons of red light, they're going to be very bright. If you only have a few photons of blue light, they're not going to be very bright. However, blue light is still more energetic than red light, and all those extra photons of red light do not add up to more energy of blue light. So it's the frequency that determines energy. It's the number of photons that determines the brightness of the light. All right. 6. A bright beam of red light, lower energy, is not able to remove an electron from an atom, but a beam of blue light, higher energy, that is not as bright, can remove